In this video we move on to 3D rendering, and we'll start with a simple CT surface and volume rendering including a VOI. Obviously 3D rendering can be useful for eye-catching images for presentation, and the 3D tool in PMOD allows you to make surface and volume renders from all modalities, as well as including VOIs. There's a dedicated segmentation interface so that you can extract the tissues that you want to render, and you can organize the segments before rendering. It's important to remember that some data types require some pre-processing. CT might benefit from masking of the imaging bed and tubes that were used for the tracer injection or for monitoring, and PET data should be resliced to the same matrix as the anatomical reference if you're using one, and that can be done easily using the Fusit tool. In this exercise we'll go straight to the 3D rendering tool without doing any additional pre-processing in the demonstration, because we've prepared the data for you. To get used to the basic principles of the 3D tool, we'll start with a single input image, and then we can combine surface and volume renderings from that CT image and add a VOI to show how you can highlight a specific organ or lesion. So within the 3D tool, we'll use the demo database and use the search field to find subject PSEG2, where you'll see 5 series. The PET3D and the CT are the original data from the scanner, and we have prepared a CT with masking of the imaging bed and a PET3D with reslicing to the CT image matrix, and that will come up in the next video. For now, I've selected the CT masked image, which I will open and then start demonstrating the segmentation. After loading, the segmentation process starts on the dedicated tab. The image is displayed on the input tab in the top left. In the lower section on the left hand side we have the methods used for segmentation, in this case the default single threshold. We have the segmentation tools, including the main workflow button in orange, and on the right hand side we have the image histogram and a list of segments once we've created some. In the top right, on the current tab, we will see the voxels that have been segmented based on the methods organized in the lower left section. CT is useful for this initial demonstration because certain tissues can be easily segmented just based on Hounsfield unit thresholds. So to do that, for the first part of the demonstration, we can enter a threshold of 500 Hounsfield units, and we have the mode set to greater than or equal to that 500 in the hope that we can segment the bones from the image. We start segmentation by clicking on the orange segmentation button, and we will see the voxels detected in the preview on the top right. There we can turn on the MIP display as usual, which can help us to see whether the segment represents what we expect it to. In this case we see the whole skeleton, so therefore the segmentation appears to be successful. To prepare that segment for rendering, we should use the green Add Segment button, which will add the settings for our segment to the Segments tab in the lower right. And here we can still adjust the properties before the actual rendering. So if we choose Set Segments 3D Rendering Properties, we can define the type of rendering. In this case, for the skeleton, I want to start with surface rendering. I can change the color using a color browser, and I will change the values to pure white. And then I can give the segment a more meaningful name, in this case, skeleton. The automatic names include the thresholding methods used, so they can be useful in themselves, but you can use something more obviously descriptive to you. So I'll confirm the change in settings for that segment, and now I can start rendering using the workflow button in the lower right. The resulting rendering can be rotated using the mouse by left-clicking and dragging, and it can be zoomed by using the mouse wheel or touchpad, or the dedicated slider on the Scene Views tab on the right-hand side. Also on the Scene Views tab, the background color can be adjusted. In this case, we have a number of preset colors and a full color browser. If I change to grey, we get slightly more contrast between the skeleton and the background for visualization. Then on the Scene Rotation tab, we can start rotating movies of our image. And like in other tools, if I activate the film strip icon, then the movie will be recorded after the next play through the rotation. As you can see, we get a save video dialog where you can choose the format that you want to use, and you can experiment with the frame rate, for example, to find the best presentation. On the right-hand toolbar, we have a capture icon, which allows you to capture 2D images also for presentation and publication with the usual save options. Next, we can add additional renderings to the overall scene, and then they will appear in addition to our SR skeleton surface rendering in the View tab on the top right. To do that, I can return to the Segmentation tab. Now, if I want to add a soft tissue segment to my rendering, I can use a different method to segment some voxels. In this case, if I change from threshold to in range in the lower left, I can enter a range of 0 to 500 Hounsfield units and then run the segmentation. Now, in the top right on the Current tab, instead of seeing the skeleton, we see all soft tissue voxels for the image and an MIP that represents that whole body look. I can add that segment to my processing list, where it appears as a second segment on the Segments tab. Then again, I can set the properties of that segment before actually rendering. In this case, I want to change from surface rendering to volume rendering using the volume HD method. I'll use the grey color table and I'll change the name to soft tissue. I should be careful not to render this segment directly because I want to add it to the rendering. This means I should turn on the append mode with the pin icon just to the left of the render selected workflow button, and now I can go on to render that soft tissue segment. So that appears overlaid on our surface rendering, and now in the top right we see two entries on the View tab for our surface rendered skeleton and the soft tissue volume rendering. If I want to adjust the display of the volume rendering, I can select it from the list in the top right. Then on the Volume tab in the lower right, we see the color transfer function and the number of settings. The top left of the settings boxes allows me to set the opacity. And if I increase that value just slightly to 0.02 and press enter to allow the update, then we'll see an increase in the opacity of our volume rendering in the rendering panel. Next, I can go on to just highlight an additional feature in the image by rendering a VOI, and this is a VOI that was previously defined in the View tool. To add that to the rendering, I should go to the Input tab in the top right. Then at the very bottom of that column, we have an option to choose the VOI that will be rendered. At the moment, it says that no volume of interest is selected, and using the Browse button for the demo database, searching for the subject that we're working with, which is PSEG2, we can see that we have a pet-derived heart VOI available. And if I set that as selected, it will be named for rendering. And then instead of the volume HD method that was just used, I can expand the rendering menu to see the VOIs options, and I can make a surface rendering of that VOI. I don't need to apply extra smoothing, so I can just confirm the rendering dialog. And then in the chest, as expected, we see the VOI appear with yellow color. illustrating how such VOIs can be added. If you want to reproduce the processing without going through all of the steps again, we'd recommend using the Save Protocol option at the bottom of the tool. In this case, a protocol identifying which images were used, which processing steps and which thresholds were used can be saved to the database so that you can recall it and reproduce everything more quickly.